Hi guys, so this video just covers question number 5 of paper 1 2015, and if you look at question number 5 you can see we've got a graphing question, and in this specific case we've got an h of x which is equal to a straight line. So we've got this straight line going over there. They've given us some of the points, they've given us the boundaries, and they've said for x on that interval, and the x-intercept is given by of h sorry, is given by q, which is this little point over here. They're saying determine the coordinates of q. That's simple. Write down the domain of the inverse, sketch the graph of the inverse. Then they're asking for which values are the inverse and the non-inverse equal, etc, etc. So let's just take a quick look at this, and we can see, because it's a straight line, it's really simple. So let's go through it. Right, so the first thing we write down is the equation. It's not f of x, it's h of x, sorry, equals 2x minus 3 along the interval x is less than or equal to 4 but greater or equal to -2. Now I'm not going to redraw it because you can just look at the paper for that, but they're saying determine the coordinates of q, and if you remember, q was the x-intercept, sorry, the x-intercept of a graph. And any graph where you've got the x-intercept, that's the guy there, you can simply see that when you want the x-intercept you must make y equals 0. So h of x must equal 0, 2x minus 3. That means we're solving for that, so 3 equals 2 of x, x equals 3 over 2. Okay, so that means that the answer for 5.1, I should have actually just written here 5.1, the answer for that is they want the actual coordinates, so it's 3 over 2, comma 0, or 1.5, comma 0. The next question they asked was write down the domain of the inverse. Now 5.2, if you guys remember what the inverse is, an inverse, if we have y equals 2x minus 3 and we look at the inverse of that, we find the inverse by simply swapping your x and your y's and then solving for y. So if we do that in this case here, what we're effectively doing when you're finding your inverse is you're flipping it around the line y equals x. So here's our line y equals x. If we've got something over here, we find the inverse, we put it over there. If we're looking at something over here, we find the inverse by putting it over there. So we're flipping it, everything goes across that line. Now that simply means, that's our y equals x line, that simply means we swap our y and x and we make our equation equal to y again. What that also means is that the range, so the range becomes the domain, pen's acting up, and the domain becomes the range. Which makes sense, because if we're swapping the x and the y, then surely the range, being the y value, and the domain being the x value, must swap if we're swapping x and y. So that's our x and that's our y. So if you know the range of the original equation, you know the domain of the inverse. And if you know the domain of the original equation, you know the range of the inverse. So there's a couple of ways you can do this. If you want to actually find the inverse, the equation of the inverse, then you can simply go, well, let's swap our x and our y. So we say x is equal to, what is it, 2y minus 3, and you solve for y, so it becomes x plus 3 equals 2y, and then y is equal to x plus 3 over 2. And then we can say, well, what is our range? We can plug in our x values. Our original x values were -2 x 4, so we plug that in, and you can see what your what your values are. Now that's if you're looking for the equation. They're not actually looking for the equation, they're just asking for the domain. So the easiest thing to do would just simply say, well, we know the domain of the original. So if we know the domain of the original, can we just calculate the range of the original? And if we know the range of the original, then we can get the domain of the new. So this is the, let's write original, and this is the inverse. So we know the domain of the original, so we know the range of the inverse. If we know the range of the original, then we can find the domain of the inverse, which would be by far the easiest. How do we find the range? Well, if we know the domain, we can plug in the extreme points, -2, -3, and we can get -7. That's the one limit. And the other limit is 4 -3. And 8 minus 3 is 5. So the range of this is between -7 and 5. So the domain of the inverse must be between -7 and 5. So the domain, I'm just going to erase this one just so avoid confusion. The new domain of the inverse is equal to -7 x 5. It's our range value. And that's that. The next question says, sketch the inverse in your answer book indicating all the blah blah blah. So let's sketch this thing. So this is 5.3. So I'm going to sketch the original, just, oh, it's a horribly skew line, just to make sure that you guys are following. So the original was fairly simple in that we had something along the lines of this. We had 4, we had q, but we know what q is. Q was 0, sorry, q was 1,5, 0, if you remember correctly. Our q value was 3/2 and 0, so 1.5 and 0. This guy here they stated was -3, and then this one here is our other extreme point, which was -2. Obviously, if we want to include these, we can say, well, this is going to be -7, as we've just calculated, and this one here is going to be +5, which we've just calculated. Alright, if we want to take the inverse of this, now I'm just going to draw a line. That's effectively the line that we're going to flip it over. Now, mine doesn't quite look correct because I've drawn it a bit not steep enough, but that's okay. But the point here is we got to flip it across that line, and we know that our domain and range swap. So our new x values are going to be our old y values, and our old y values are going to be our new x values. So everything swaps. So if we had to draw this, I'm going to draw it in red. We simply say, well, we now go to -7, and 5. Let's put it over here, 5. And on the y-axis, we go to -2, which is somewhere down over here. So we had -7 and -2. And we're at 5 and 4. So we can just go all the way up to 4. Remember, everything's changed. Now, I'm literally looking at the graph and I'm drawing the inverse. Obviously, you can plot this equation here. That one you can do as well. No problem. And then which are the points that we go through? Well, if we went through 3 here, -3, we've got to go through -3 over here. And if we went through 1.5 there, we've got to go through 1.5 on the y-axis. So literally all your x's and all your y's swap around. Okay, my graph is not particularly straight, and like I said, it doesn't look quite right because I've drawn them a bit skew, but that's your new graph. That's your h, -1, and obviously the black one was your h. Now, just to reiterate, I literally drew it based off reading the graph, not knowing the equation, and just swapping all your x's and all your y's. So all your x's become y's, all your y's become x's, and that goes for the intercepts and the extreme points. If you didn't want to do that, you could simply look at the original equation, take the inverse of that equation, which is this y equals x plus 3/2, and draw that as if you're drawing a straight line graph, and you can't get that wrong. You've done that since grade 3, so there's no excuse for not being able to draw that. And that's pretty much it. I don't think they want anything else, so let's go to the next question. It says, for which values of x will the original graph equal the inverse? So the question says 5.4, switch black again, 5.4, for which values of h of x, the original graph, will equal h -1 of x? Which values of the original graph will equal the inverse? Well, we know what the original graph equation was. The original graph equation was y equals 2x minus 3. I think it's correct. Y equals 2x minus 3 up over here. And our new equation for the inverse, as we already calculated, if you didn't calculate that before, you'll have to do it now, x plus 3/2, and y equals x plus 3/2. And they're saying for when are they equal? Well, we make them equal then. So 2x minus 3 is equal to x plus 3 divided by 2. And we simply solve for x. So we multiply everything by 2 to get rid of that 2 at the bottom. And whatever you do to the one side, do to the other side. Now, just one thing. If you ever multiply something like that, always put brackets, because you have to multiply the entire side, not just one. And if you forget brackets, sometimes people forget the basic rules. So always put brackets. 2 times 2x is 4x. 2 times minus 3 is minus 6. And this 2 cancels with that 2, which is the whole point of why we did it. So x plus 3. I like to keep the x's positive, so I'm going to take that guy across. And 4 minus x, because there's a plus here, so it becomes a minus. It's 3x. And the 6 goes to the other side, so that's equal to 3 plus 6, which is 9. X equals, so we divide both sides by 3, divide by 3. 3's cancel, x equals 9 divided by 3 is just 3. So we have x equals 3. And at x equals 3, we get an interception. And obviously there's only going to be one interception because it's a straight line. So there is only one interception. And they're only asking for the x value. If they wanted the y value at which it intersected, you would have to then substitute that back into either of the two equations. Also, if you want to check that what you've done is correct, we can simply substitute that back in, and we have to get the same value for both equations. So y equals 2, I'll plug in 3 minus 3, 6 minus 3 is just 3. And then I plug into this equation to check 3 plus 3 over 2, which is 6 over 2, which is 3. So we see we get exactly the same y value, which we have to because it's the same point. The next question, number 5.5, I think I'm going to show you this one rather than discuss it because it's a bit long. But it says p of x and y, and the p is this point here. So p of x of x comma y is the point on the graph h that is closest to the origin. Calculate the distance. That's when they say closest to, that is a minimizing equation. So we need to minimize this thing. Now, if we just look at a rough graph, they say, make it a little bit bigger so I can actually write on the damn thing. So effectively we've got this where that's point P, x comma y. We know the equation y equals 2x minus 3, and that's what we have. Now what is the distance between the origin 0, 0, 0 and P? It looks like a theta, so let's make that a 0. So the distance formula, we know that the distance OP is equal to the square root of that one plus, or that one minus that one. So in this case it's 0 minus x, which is squared, so it's just x squared plus y squared. Obviously your distance formula, your original distance formula d is equal to the square root x1 minus x2 squared plus y1 minus y2 squared. You can get that off your formula sheet, or you can just remember it. You should remember it by now. And because we're minusing 0 or plusing 0, it's just those values for p. And you square it, so the negatives disappear. So we end up with this, and this is just a basic Pythagoras equation. So they want the distance, it says the closest to the origin. So we want to minimize this distance. So the distance needs to be minimized. Now, that means we have to derive. But what do we derive with respect to? Well, we can't derive with respect to x and y. So we've got to think now. Can we write this in a way that leaves only x's or only y's? Well, of course. We know what the y value is. That y value is equal to 2x minus 3. I mean, that's what the original equation was. So we substitute that in, and we see we get x squared plus 2x minus 3 squared. We then square all these things out and we work them out, and we say, okay, what does that give us? Now the square root might look big and ugly, but it doesn't matter because we'll get rid of that square root. X squared plus, and then this one, 2x minus 3 times 2x minus 3. Let's just work that out so we don't get into a mess. 2x times 2x is 4x squared. That 2x times negative 3 is negative 6x, negative 6x plus 9. So we have 4x squared minus 12x plus 9. So we plug that in, so we have 4x squared minus 12x plus 9. So hopefully I haven't made a mistake there. And we can then simplify that further and say that's 5x squared minus 12x plus 9. So we've now got our simplified version of everything in terms of x. And we say, okay, well, if that's our simplified version, then what do we do next? We know we've got to derive. That is one horrible thing to derive because of that square root. But surely, if what is underneath the square root is a minimum, then when you square root the minimum, you get the minimum. And if what's underneath the square root is a maximum, then if you square root it, you're still getting the maximum. So it doesn't actually matter whether that square root is there or not, because we're minimizing or maximizing. We're trying to find what is the minimum value that this will give us. And surely if we find the minimum inside value, when we square that value, we'll get the minimum outside value. So we don't actually care about that square root. So we can drop it completely. And we can say OP is equal to, now we got to derive it, so OP dash is equal to, and just bear in mind we're squaring both sides. So maybe we should write this a little bit differently, just to note that we are square rooting it. So it becomes OP squared is equal to 5x squared minus 12x plus 9. And like I say, the reason why we square it is simply because that square root, when we're looking for the maximum or minimum, doesn't make a difference. If we find the maximum here, then when we square it, it's going to still be the maximum. If we find the minimum here, we square, it's still going to be the maximum, or sorry, the minimum. Obviously, we're not looking for, we've got to be careful in that case about the positives and negatives, but it doesn't matter in this because whatever we find to be the correct answer is going to be the correct answer for that one as well. Okay, so normally when you see something like this and you've got that horrible square root, we can drop the square root because we're maximizing or minimizing. So, OP squared derived, we're deriving that whole thing, is equal to 10x minus 12. We set that to 0, because remember, we're finding the gradient when the gradient is 0. In other words, if we have something that looks like that, we're finding when the gradient is 0, so we find the maximum point, and that's equal to 10x minus 12. Take that across, 12 equals 10x, x equals 12 divided by 10, which is 6 over 5. 6 over 5. So we've now got our 6 over 5, and that's our x value. That is the maximum. That is when, so effectively we found this. 6 over 5. Now we've got to substitute into our original, because when we get our maximum value, or when we get our derived value set to 0, like this one, we substitute that back into the original equation, because that's what we're working with. And the original equation is this guy here. So we simply see that OP, now remember, we're not looking at OP squared anymore, we're looking at the original equation. So we found that this equation, OP, the distance, is minimized or maximized, in this case minimized, when, so this is actually a happy face, not a sad face. Maybe I should actually just redraw it as a happy face. It's actually +9, so let's just draw the whole damn thing correctly. And they're saying, well, there's our minimum. Gee, it's shifted. So there's our minimum value, and that value is at 6 over 5. What is that y value? So if we want that y value, we simply have to say, well, if we know the x value is 6 over 5, plug that into our original equation, we get the y value. So OP is equal to the square root of 6 over 5 squared minus 12 times 6 over 5 plus 9. And we plug all those guys in, and we end up with square root 3 over square root 5, or you just use your calculator, 1.34 units. And that's awesome. So this is not a particularly difficult question, but you have to realize that this square root can be ignored when you're deriving, because if you minimize the inner part, the outer part is automatically minimized with it. So we drop that square root to make it much easier to actually work with. If you had kept that square root in, this thing becomes an absolute nightmare. Okay, so it's one of those little tricks that you need to remember how to do, and then go for it like that. There are other ways in which you can do it, but I would prefer not to go over it. Yeah. Okay, if you want to look at other ways, you can either ask me directly, PM me, or look at the memo. But I find this is the most convenient way to do it. If you ever want to maximize or minimize, the best thing to do is derive. Okay, question number 5.6. Okay, let's actually take a look at question number 5.6. Question number 5.6 says h of x is equal to f dash of x, so the derivative, where f is a function defined for that. So it's on the same, it's exactly the same, just f is the derivative of h of x. Explain why f of x has a local minimum, and then write down the value of the maximum gradient of the tangent to the graph. Okay, it's not very nice. So how on earth do we do that? Well, there's nothing complicated about that either. If we look at a h of x, and we say h of x is equal to, or sorry, yeah, it says h of x is equal to the derivative of f of x. What they're actually saying is, let me just write 5.6. When we take a derivative, let's go y equals 2x squared plus, actually let's choose one that makes complete sense. Let's just leave it as, okay, x squared minus 3x for argument's sake. That's our equation, and when we derive that, we take y dash is equal to 2x minus 3. Okay, I'll make it plus as a constant here, so plus 6 for argument's sake, and we've got that. That's our equation. So what they're saying here is exactly that. They're saying h of x, which was the original equation that we were working with, if you remember correctly, that is this one over here. That's h of x. And they're saying h of x is the derivative of some random function f of x. That random function is this one over here. Okay, so if that is f of x, this one over here, and h of x is this one, then h of x must equal the derivative of f of x. That is what they're saying. And they're saying specifically here, explain why the function f, which is the original, this is function f, why that has a local minimum. How do we know that? Well, two ways. We know that because if you look at the graph of h of x, and that's our graph, is that increasing or decreasing? Well, it's increasing. It's always increasing. And if you look at a parabola, and in this case I'm going to draw this parabola over here because that's the thing that we'd have. And I've just chosen some random plus 6, but let's say it didn't have a plus 6. You're going to end up something along these lines. Plus 0. So if this 6 was a 0. And you can see it goes from a negative gradient on this side. It hits a 0 point, and then your gradient becomes positive. So if you see a straight line that goes with a positive gradient, m bigger than 0, we know that it's a happy-faced parabola. So this guy here, this h of x, is the derivative of a happy-faced parabola because we have a positive gradient. If we had a negative gradient, that means that we start off with a positive. Okay, remember the gradient here, this m is less than 0. So if we look, the gradient is, obviously the gradient stays the same on the straight line, but the values are positive. So the y values on this side here, positive, 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 we hit a 0 point, and then they become negative. So the gradient is positive, 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 then the gradient becomes 0. That's at this 0 point. Then the gradient goes negative, 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 because we have a negative y value there. So what this means is if your gradient, so if your derivative has a positive gradient, we have a happy face. So let me just write happy face parabola. And if your derivative gradient is negative, we have a sad face. Parabola. So, I'll probably do another video on this just to elaborate a little bit more and to describe it a little bit better, but that's effectively it. So the question was, explain why f of x or f has a local minimum. Well, the simple fact that we have a happy face derivative, a happy gradient, there's a positive gradient. So the simple fact that we have a positive gradient tells us that we have a happy face parabola, and a happy face parabola has a local minimum. So I don't know how you want to actually describe that. I would describe it simply saying it has a local minimum because the derivative has a positive gradient. And you can look at the memo for the different exact wordings. And there's, if you read the memo, it says f is decreasing on the left and increasing on the right, which is exactly what we explained. It's decreasing over here but increasing over there. So yes, it is. I don't know if I can erase these lines here. Okay, so it is decreasing and then increasing. It's a happy face because we have a positive gradient over there. Okay, and yeah, they've got one of the answers that they give here is they simply say f has a minimum since a, which is this guy here, is greater than 0. You can use a, m. I would literally write out the gradient. Gradient of h of x is greater than 0. Okay. Then the next one, they ask, write down the value of the maximum gradient of the tangent. So what is the maximum value? Well, you literally look at your graph, h of x, and you say, well, when is h of x at a maximum? And this, okay, well, pen is not playing nicely. So when is this thing at a maximum? Well, we know when this thing's at a maximum because you know what the graph looks like. The graph looks like that, and we have our maximum and our minimums. We calculated this earlier. This was 4, that was 5, this was it 2 and minus 2 and minus 7? So we can see the minimum is minus 7 and the maximum must be 5. So we can literally state that the maximum gradient of f of x, which is equal to f of x dash, the maximum gradient, well, I suppose the way I've worded it, the maximum gradient of that is equal to 5. And we get that because we say f dash of x, which is the gradient, is equal to h of x, and h of x is a maximum on this interval at y equals 5. And that's it. That is question number 5 done, I think.